in today's video, we are going to be looking at numerical differentiation in numerical analysis. Now, numerical differentiation is simply a numerical technique which is used to approximate the derivative of a given function at a given point using a data table. Now, this table can be categorized into three. We have the forward difference table, we have the backward difference table, and then we have the central difference table. An understanding of these three tables is key and important if you must understand numerical differentiation in numerical analysis. So let's explain the difference between the central difference table, the backward difference table, and the forward difference table. Now let's take a look at this table on the board. We have a table of values x, which is 1, 2, 3, 4, 5. You have f of x. Mind you, f of x here simply means y, okay? F of x is simply equal to y. So these are the values of y, 3, 6, 9, 2, and 15. Now this simply means that when x is 1, y is equal to 3. And when x is 2, y is equal to 6, and so on. Now, which part of this table represents the forward table, which part of this table represents the backward table, and which part of this table represents the central table? Now, if you exclude the table that contains x and y, let us consider only the part with real values, which is 1, 2, 3, 4, and 5, which means this part is categorized into 5 places. So I can bisect this table. I will have from here, which is the first two, then I will have the last two, then I have a central. Okay, any value of x that lies between the first two is said to be at the center, at the forward of the table. So this is called the forward difference table. Okay, any value that lies at the forward between 1 and 2 is said to be at the forward of the table, whereas any value that lies between 4 and 5 is said to be at the back of the table. So this is the backward table. Okay, so this is the backward table, and any value that lies at the middle is said to be the central table. So the middle here is said to be the central table. Okay, so mind you, value between 1 and 2 is at the forward of the table, values between 4 and 5 is at the backward of the table, whereas values in 3 or between 3 is simply at the center of the table. Okay, so let's say we are asked to approximate the derivative when x is equal to 1. You see, if you're asked to approximate the derivative when x is equal to 1, 1 is directly at the forward of the table. So this simply means you're going to be using the forward difference method to approximate that derivative. If you're asked to approximate when x is simply 1.5, again, the highest value of the forward table ends at 2. So which means 1.5 still lies between 1 and 2, and this still lies at the forward of the table. So if you're asked to approximate when x is 1.5, it also means that you're going to be using the forward difference method to approximate that derivative. Now, let's say you're asked to approximate when x is equal to 2.1. So it is very, very important at this point for you to understand that the value of the forward difference table or the forward table ends at 2. So anything beyond 2 means it has now started entering into the central table. So if x is simply 2.1, it means it has eclipsed 2 and now approaching 3. In that case, we are going to be using what? The central difference formula to approximate that derivative. Okay, so this also means that if you have to approximate the derivative when x is equal to 3.1, it also means that 3.1, because the central difference table ends at where? 3. So anything beyond 3 means it is now encroaching into the back of the table. So 3.1 is directly encroaching into the back of the table, which means we are going to be using the backward difference method to approximate that derivative. All right, so if you have to approximate when x is equal to 4.5, you see 4.5 lies between 4 and 5, which is at the back of the table. So which means you're going to be using the backward difference table once again to approximate that derivative. Okay, so now that you understand the difference between the forward, central, and backward difference table, let us now pick each of these tables individually and analyze the formula that can be used to approximate their respective derivative. And for this video, we are going to be giving up to the third degree derivative. Okay, so let's start with the forward difference table. Okay, what is then the forward difference formula or method? So we have said that if the value of x to be approximated lie at the forward of the table or at the beginning of the table, we simply use the forward difference method. What then is the forward difference method? For the first derivative, the y all over the x is given simply as f of x plus h minus f of x divided by h, where h is a term called a step size or simply interval. H is a term called a step size or simply interval, and it is simply the difference between successive values of x. Now, what does that mean? That simply means for this given table, h is equal to, it can be x2 minus x1, or h can be x3 minus x2. So it means difference between successive values of x. It can also be what? X4 minus x3 or x5 minus x4, and the value will remain constant. Okay, so for instance, for this given table, h is going to be equal to x2 is 2 and x1 is 1. So you can simply say 2 minus 1, and this is equal to 1. Or you can simply say h is also going to be x3 minus x2. x3 is 3 minus x2 is 2. 3 minus 2 is also going to give you what? 1. So h, that simply means the step size or the interval, and it is obtained from the value of x. Okay, so you use this formula to approximate the first derivative. For the second derivative approximation, you have the squared y all over the x squared. This is going to be equal to f of x plus 2h for the forward difference table or the forward difference method, okay, minus 2f of x plus h plus f of x all over, you square the interval, all over h squared. So this is a formula to approximate the double derivative using the forward difference method. Okay, once again, their values remains what you already know. For the third derivative, which is where I'll stop, you have the cube y all over the x cube. This is going to be equal to, so you simply have f of x plus 3h, okay, minus 3f of x plus 2h plus 3f of x plus h minus f of x all over h cubed. So this is the formula to approximate the third derivative. Now, there is something unique about this formula that you need to know. Once you pick out your first function, f of x plus h means you're starting. That's your first derivative. But for the second derivative, it starts with f of x plus 2 now multiplied by the interval. And for the third derivative, f of x plus 3 now multiplied by the interval. So you have f of x plus 3h. Now, what is then the unique thing? After the first functions, the next is always going to be minus. Then it interchanges to plus, minus, and so on. So you see f of x plus h minus f of x. For the second derivative approximation, you have f of x plus 2h minus 2f of x plus h plus f of x. So you have minus comes first before plus, and then minus, and so on. So over here you have f of x plus 3h for the third derivative minus 3f of x plus 2h plus 3f of x plus h minus. So it moves from plus, minus, so it moves from minus, plus, minus, and so on. So the same approach can also be used for the backward difference method. Now, let us understand the formula for the backward difference method. Let's take it out. For the backward difference method, okay, backward difference method. So it's basically the same thing with the forward difference method. The only difference now is that the backward difference method starts the formula from behind. The backward difference method is the same formula as the forward difference method, but the only difference is that it starts the formula from behind, and it also maintains the same principle of after the first function, you start with negative to positive to negative and so on. Now let's pick out these formulas and see. We're going to pick the backward difference formula from the forward. Okay, so for the first derivative approximation, dy all over the x, this is going to be equal to, so you start from the back. The back here is f of x. So you simply put down f of x. Now, the sign will still remain minus because after the function, the next is minus. And here is minus, so it goes minus f of In this case, now instead of x plus h, it becomes x minus h because it is taking the function or the formula from behind. That's why it's called backward all over h. So this becomes the first derivative approximation of the backward difference formula. So you see, it starts the formula from behind and changes in the bracket, it changes the positives into what? Negative, because you're moving from behind. Let's start the second derivative approximation and see. So you have the squared y all over the x squared. This is going to be equal to, for the second derivative approximation, again, you start from behind. You have f of x there. So you put it out, f of x. So instead of plus here, remember the sign must start with minus for both cases. So it becomes minus. Then you move to the next value, 2f of x, but this is no longer going to be f of x plus h. It becomes f of x minus h, because you're not talking about the backward difference method, right? So this becomes minus 2f of x minus h. So you know, after minus, next is plus. Then you start again. After minus, next is plus. Then the remaining value function there is f of x plus 2h. But now you're going to change this plus to what? Negative. So you simply have f of x, okay, plus f of x minus 2h all over h squared. So you see that the formula is basically the same thing, but in the backward difference method, you're starting from behind, okay, and then moving forward. So which means our third derivative approximation, the cube x all over the x cube, is going to be equal to, so you look at the forward difference method for the third derivative, you start from behind. You have f of x, you put it down, f of x, the next sign there should be minus. Then after that minus, you have 3f of x plus h, but you're going to be changing the x plus h inside to become x minus h, because you're talking about the backward difference, right? So this becomes minus 3f of x minus h. Next should be plus. Then the next value after this is 3f of x plus 2h, but you change this positive sign here to be negative, right? So it becomes 3f of x minus 2h. And finally, you have f of x plus 3h. And remember, if here is plus, the next value there should be, next sign there should be negative, right? And then instead of f of x plus 3h, it becomes f of x minus 3h. So you have f of x minus 3h, okay, all over h cube. Okay, so this is how to obtain the formula to approximate what? The differentiation for the backward difference method and for the forward difference method. And finally, I will state the formula for the central difference method. And at the end, we are going to be solving an example to explain all of this. And at the end of this video, I promise to give an assignment, which I bet is going to give you a little shake. And I want you guys to also attempt it and send to my DM on WhatsApp. Okay, so let's move now to the central difference formula. Now, for the central difference, since it lies at the center, it means it pulls value from the forward table and it pulls value from the backward table to make up its derivative. Now, the first derivative approximation is going to be dy all over the x. This is now for the central difference. Central difference method. Okay. So the first derivative becomes, you have f of x plus h, which is at the forward of the table, minus f of x minus h, now at the back of the table, divides by 2h. So you see how this formula is. It picks a formula or a function from the forward of the table and picks from the back of the table to form what? The central difference method. So this is the first derivative approximation, and this is the formula you use, right? Now, for the second derivative approximation, the squared y all over the x squared, this is going to be equal to, again, you have f of x plus h minus 2f of x plus f of x minus h all over h squared. So this is the formula for the second derivative approximation using the central difference method. So like I said, the central difference method actually pulls a value from the backward difference table and from the forward difference table and use it to combine to form its what? Derivative. And finally, for the third derivative, the cube y all over the x cube using the central difference method is equal to, you have f of x plus 2h minus 2f of x plus h plus 2f of x minus h minus f of x minus 2h all over 2h cubed. So you see how it plays. For the third derivative approximation, you have f of x plus 2h from the forward table minus now a step down to f of x plus h still at the forward table. Now plus you start reducing f of x minus h instead of plus h. This is now at the back of the table, and then f of h x minus 2h also at the back of the table. So these are the formulas you use to approximate the first the forward difference table, the backward difference table, and the central difference table. And we're going to be using these formulas now to solve an example. So do not be in a hurry, sit tight and watch this video through the end. And like I said, at the end, I'm going to be leaving you with an assignment, and I hope you solve them and send to my WhatsApp, or you can also post the answers at the comment section. All right, so let's say we're using this same table as an example to our explanations. Let's say we're asked to approximate the derivative, the first and second derivative, the y all over the x, and the squared y all over the x squared when x, okay, when x is equal to 2. So let's say we're asked to find the first and second derivative approximation when x is equal to 2. Okay, in that case, once again, you take a look at the table. You already know how to where 2 falls. 2 falls at the forward of the table. It simply means we're going to be using the forward difference method to approximate this derivative, not the backward and not the central, because the point of interest 2 is at the forward of the table. Okay, so remember the formula for the first derivative. The y all over the x is equal to f of x plus h minus f of x all over h. So we need to find our step size h, or the interval. So the interval h is equal to, it can be x2 minus x1, or it can be x3 minus x2, and so on. So x2 there is 2, x1 is 1. So you simply have 2 minus 1. So this simply implies that my interval h is equal to 1. Now, having found 1, the next thing to do is to find f of x plus h. So we find f of x plus h, where x here is the point of interest given to us in the question. It says when x is equal to 2, so it means x is equal to 2. So you simply have f of 2 plus h. We found h to be 1, so it becomes f of 2 plus 1. This is going to be equal to what? F of 3. So this means that when x is 3, what is the value of y, right? So you go to the table, when x is 3, y is equal to what? 9. So this simply means that f of 3 is equal to 9. Simple. The next thing there in the formula is f of x. So you simply find f of x. And what is x? The point of interest. And for this question, x is equal to 2. So you have f of 2. And from the table, it simply means when x is 2, what is y? When x is 2, y is simply what? 6. So f of 2 is equal to 6. You have your values ready. You plug into the equation. Therefore, your first derivative, the y all over the x, is going to be equal to f of x plus h gave us what? 9. So you simply have 9 minus f of 2 gave us, or f of x gave us 6, divided by h. H is 1. So this is actually what? 9 minus 6 is 3 divided by 1. This implies that the first derivative approximation, the y all over the x, is equal to 3. And you have this. It's as simple as this. So to approximate the second derivative, remember the formula, it is here. So we have f of x plus 2h minus f of x plus h plus f of x. So we know what f of x is. We need to now find f of x plus 2h, because we already know what f of x plus h is, right? So let's find f of x plus h. Okay, so for the second derivative test, look, this is the formula here. Let's find f of x plus 2h. So we find f of x plus 2h. This is equal to f. X now is the point of interest for the question is 2, plus 2 times h is the step size, which is 1. Okay, so this is equal to f into, this is going to be 2 plus 2 times 1 is 2. So this is 2. So this simply implies that f of x plus 2h, okay, is actually f of 4 because 2 plus 2 here is 4. So this means you go to the table when f of x or when x is equal to 4. What is the value of y? Value here is 12. So f of 4 is simply what? 12. Okay. So I think I've wiped f of x plus h, but we can quickly do that. So once again, f of x plus h, you already know this is going to be f into x is 2, h is 1. This is going to be f of 3. And f of 3 means when x is 3, what is the value of y? And that is 9. So you have this to be 9. And finally, you have on the formula f of x, which is f of 2. F of x is actually f of 2, yeah, because x is actually 2. So when x is 2, what is y? 6. You have 6. So you have all your points. You simply represent them into that equation to obtain the second derivative, right? So you have d squared y all over the x squared to now be equal to, the formula says f of x plus 2h, and we know our f of x plus 2h to be what? To be 12. So you simply put it down, 12 minus, you have here minus 2 times f of x plus h. So remember, 2 times f of x plus h, that gave us 9. So you have 2 times 9, okay, plus you have here f of x, and f of x simply gave us what? 6 divided by h squared, and h is 1, so it becomes 1 squared. So this is going to be equal to 12 minus 2 times 9 is 18 plus 6 all over 1 squared remains 1. So the squared y all over the x squared is going to be equal to, so we simply compute 12 minus 18, that is minus 6 plus 6, and that is simply 0. So it means the answer to this question is 0. So the second derivative approximation is simply 0. So the squared y all over the x squared when x is equal to 2 is simply 0. So you can still use the same approach to find the third derivative. So this is going to be like an assignment. So you guys should try it and send the answer on the comment section. All right. Now, let's try out for the backward difference and see how that works, right? Let's solve an example. Let us now say we're asked to find the y over the x plus the squared y over the x squared when x is actually 4. Okay, so if x is 4, you already know 4 lies at the back of the table. This simply means we are going to be employing the backward difference method. A second, please. All right, so when x is equal to 4, it means 4 is at the back of the table. So that simply means we are going to be using the backward difference method to solving this. Now, I know someone might have a question in mind, like what if when x is 1.5, or what if when x is 3.5, or even 3.1 or 4.1 or so and so on. Now, that question will be answered at the end of the video. So do well to watch the video to the end so you can have an answer to that particular question. All right, so let's move on. So for the backward difference, remember the formula, the y all over the x, the first derivative becomes f of x minus f of x minus h all over h. So we know what our h is. We'll find the value as 1. Okay, so we know what f of x is. F of x is going to be f of the point now is 4. So it becomes f of 4. What is the value of x when, sorry, what is the value of y when x is 4? That's what it means. So this is when x is 4. The value here is simply 12. So f of 4 is simply what? 12. And you have this. Similarly, we find f of x minus h. So you have f of x minus h. This is going to be equal to f of x there is 4, h there is 1. So it becomes f of 4 minus 1. This is equal to f of 3. So this means from the table, when x is 3, what is y? When x is 3, the value of y is simply 9. So f of 3 there is 9. So you compute your derivative. This simply implies now that the y all over the x is going to be equal to f of x, which is f of 4 is 12. So you have 12 minus f of x minus h. That simply gave us 9. So that's 12 minus 9 all over 1, which is actually 3 divided by 1. So this implies that for the backward difference method, the y all over the x is equal to 3. And you have this. Okay, so we now move to the second derivative approximation. So if you look at the formula, again, you have f of x minus h. We already have this value, so we're going to be keeping this. F of x minus h is here as 9. We also have f of x from that formula, f of x minus h. So all we need to find now is f of x minus 2h, right? So we simply look for f of x minus 2h, okay? So f of x minus 2h is going to be equal to f. X there is a point of interest, which is 4, minus 2 times h there is 1. So this is going to be f of 4 minus 2 times 1 is 2. This simply gives us f of 2. So this implies that f of x minus 2h is actually f of 2. So which means from the table, when x is 2, what is y? Value there is 6. So f of 2 is simply 6. So with this, you can now find your second derivative test. The squared y all over the x squared. This is going to be equal to, so from the formula, we said f of x, and f of x will have the value to be 12. So you put it down, 12 minus 2 times, okay, minus 2 times f of x minus h. And you know what f of x minus h is? Value is 9. So minus 2 times 9 plus 2, okay, plus f of x minus 2h. So plus f of x minus 2h, and f of x minus 2h gave us here as 6. So plus 6 all over h squared, which is 1 squared. So this is equal to 12 minus 18, plus 2 times 9 is 18, plus 6 all over 1. And this also gives us what? 0. So for the backward difference, when x is equal to 4, the double derivative is simply 0. So you can still employ the same approach for the third derivative. So this is also going to be an assignment. So in all, you have 2 assignments so far. So you can do it and post on the comment section, or you can do it and share it to my WhatsApp number displaying right up there. Okay, so let's try another example to explain the central difference method, and that will be the end of the video. Then I will answer the question which I asked earlier: what happens when x is 1.5 or even 1.1, or when x is 3.1, or when x is even 2.1 or 2.5? I will answer that at the end of the video, so stay tuned till the end. All right, so let's say we're asked to find the first and second derivative when x is equal to 3. So now you see that 3 is directly at the center of the table, which means we are going to be employing the central difference method, right? Okay, so you remember the first derivative for the central difference method, the y all over the x is simply equal to f of x plus h minus f of x minus h all over 2h. Okay, so we simply find f of x plus h. So the interval remains the same, 1. So f of x plus h is equal to f of x is a point of interest, which is 3, plus h is 1. That is simply f of 4. So which means when x is equal to 4, the value of x here is 12. The value of y, sorry, is 12. So f of 4 is simply what? 12. Again, you find f of x minus h. So f of x minus h equals f of x there is 3 minus h is 1. That is simply f of 2. So when x is 2, what is y? Value is 6. So you have this to be 6. So which means the first derivative, the y all over the x, is going to be equal to, compute them into this equation, f of x plus h gave us 12. You have 12 minus f of x minus h, that gives us 6. You have 6 all over 2 times the interval is 1, 2h. So this is equal to 12 minus 6 there is what? 6. All over 2h there is 2. And this device simply gives you what? 3. Now, if you observe, all the derivatives we've done so far have been the same. First derivative using backward difference method is 3. The first derivative using forward difference method also 3. Now using central difference method is also 3, which means for this given table, we are very much correct. It means we are very much correct because the first derivative are appearing to be what? The same. Even at different points, it is the same. Okay, so it means we are very much in order. Okay, so without even solving, you should know that the second derivative approximation using the central difference method is going to be what? 0, because we've had it to be 0 in the other cases. But let's solve it and see. Okay. So for the second derivative approximation using the central difference, the squared 1 over the x squared, remember the formula, it is simply f of x plus h minus 2f of x plus f of x minus h all over h squared. So let's try this. Let's put in our value. So I've already kept the value of f of x plus h. We did that earlier. Value is 12 and f of x minus h value is 6. So we know what f of x is. So let's simply find f of x. Here f of x is going to be equal to f of the function there is 3, x there is 3. So that's f of 3. So what's the value of y when x is 3? Value there is simply 9. When x is 3, the value is 9. So you have it to be 9. So let's plug all of this into the formula. This means that d squared y all over the x squared is going to be equal to f of x plus h. The value is 12. Okay, so you have 12 minus 2f of x. F of x here give us 9. So minus 9, 2 times 9 plus f of x minus h. That gives us here 6. So plus 6 all over h is 1. So 1 squared. So this is going to be equal to 12 minus 2 times 9 once again is 18 plus 6 all over 1. So you see that the double derivative, the squared y all over the x squared is equal to 0, which also matches the answers we've obtained previously using the forward and the backward difference method. So at each point on this table, the first derivative approximation is 3. The second derivative approximation is 0. And the third derivative approximation have been given to you as an assignment. So do it and post on the comment section, or you can share it to my WhatsApp number displaying up there. Okay. Now, for this given central difference method as well, you can as well attempt the third derivative approximation. I'm just going to display the formula on the screen right here so you can see it. Use it and approximate the third derivative using the central difference method. Okay, so to answer the question which I said, what if when x, if you're asked to approximate derivative when x is equal to 1.5, or when x is equal to 2.1, and when x is equal to, let's say, 3.5, something like this. So you see that if x is 1.5, if you're to look for the value of f of 1.5, is actually not on the table. You observe that f of 1.5 is not on this table. So which means that you have to 1.5 lie between 1 and 2. In that case, you have to what? Interpolate. So that brings us to another idea of finite difference, or another idea of numerical differentiation. That is called the finite difference method. In that case, you have to what? Carry out a difference table. You have to form a difference table for interpolation. So that brings us to the whole concept of numerical interpolation, or interpolation in numerical analysis. So I've done numerous of videos on numerical interpolation. You can look at my channel playlist and you're going to find numerical methods playlist. In that playlist, you will find everything you need to know about numerical interpolation: forward difference interpolation, backward difference interpolation, the central interpolation, and the Lagrange interpolation, and all of that. They are all captured in that playlist. I'm going to be dropping a link of that playlist also in the description of this video so you can watch for proper understanding. But I will also do a separate video again to re-explain the concept of interpolation and how you can be able to answer such a question when the value of given to you is not on the table. In that case, it means you have to interpolate, and you have to use the idea of interpolation in numerical methods to do that. But in all, the idea of forward, backward, and central difference method is still maintained for both interpolation and for numerical differentiation. All right, guys, so I hope you find this video very interesting and helpful. Please, if you do, I would like you to like this video, comment nicely, share to your friends, and if you're new to the channel, do well to tap the subscribe button right now and turn on your notification bell so you don't miss out on the next video when it drops. I will see you in the next video. Cheers.